Okay, so today we're going to try and finish up the last of the graph algorithms, which is the all pair shortest path algorithm by Floyd-Warshall. I'm going to give you a little bit of the intuition and then show you the code. Uh, so we may finish a little early today. Let's see how this goes. Here we go. All right, so what we said last time, give me a second. What we said last time was that one way of doing all pair shortest path is to run single source shortest path algorithm from every vertex. And so essentially you'll run Dijkstra's, except that you will try every possible source. At the end of this whole process, you would have the shortest path from every source to every other vertex. And so therefore you'll have the all pair shortest path. Now, if you wanted to do this, if you wanted to invoke Dijkstra's algorithm n times, the running time becomes something like m times n plus n squared log n, which is not too bad, but the algorithm, Dijkstra's algorithm is quite complex, and you have to use these fancy data structures like a priority queue. So overall, it turns out to be a little bit more work than is necessary. What we're going to look at today is a much simpler algorithm that uses something called dynamic programming. We won't learn dynamic programming today, but you will see later on, because we'll be starting with dynamic programming next. What you'll see is that the approach used by Floyd-Warshall is almost exactly what you would do if you were solving this using a dynamic programming approach. Now, one of the tricks of using this approach on the all pair shortest path algorithm is shown in this picture. We're going to solve the problem in stages. And in fact, there are going to be n stages. And in the kth stage, we are going to solve the following problem that says, let's find the shortest path between every pair of vertices, in this case from I to j, and allow only intermediate vertices from a limited set. And the limited set in this case is going to be the vertices 1, 2, 3, all the way up to k. And by changing the value of k, we can limit the scope of the problem that we're going to be working with. So that's the general idea here. And so what you'll see is that we only allow intermediate vertices from this set. However, when you start to think about this, and when you actually look at the algorithm, the path, there are really two possibilities. One is that the shortest path goes through the vertex k, or it's possible that it doesn't go through the vertex k. If it doesn't go through the vertex k, then clearly all the intermediate vertices are only going to be in the range 1 through k minus 1. On the other hand, even if it does go through k, you can break it up into two paths where each of these subpaths only use intermediate vertices from the set 1 through k minus 1. So what we are saying is that the shortest path between any pair of vertices that use the intermediate vertices 1 through k can be broken down into at most two paths, where each of these paths only uses intermediate vertices in the range 1 through k minus 1. And because of this property, it turns out that you can solve this in a nice iterative fashion, which turns out to be the basic idea behind dynamic programming. So using this picture, we can now design the algorithm in a fairly systematic way, and we're going to do the following. We're going to build these matrices, which we will call as dk. Well, actually, it's d superscript k as shown in this picture here, where D superscript K is the set of all shortest path lengths between every pair of vertices. So because it's a matrix, you get all such pairs, but it's only going to be shortest paths for which the intermediate vertices are from the set 1 to 3 up to K. When K is small, you don't have too many choices for the paths. When K gets larger and larger, you get more and more options. And when K equals N, essentially you're allowed to try out any possible path. And so therefore, the information you will have will be the genuine matrix of shortest path lengths between vertices I and J for every such pair. So that's the idea here. We are going to build these matrices that are shown here. Based on this definition, D of 0 is going to be the matrix of shortest paths between any pair of vertices for which all the intermediate vertices are in the set. Remember, if K is 0, really the set is just the empty set. So we are not allowed to use any intermediate vertices, which means either we can use an existing edge or we just don't use an edge. So therefore, it turns out that D super 0 can be written down quite easily. It's simply the set of weighted edges that are present in the network, and we can put those down quite easily. In this case, we're assuming that the network looks exactly as is described here. Namely, there's the first row corresponds to vertex 1, vertex 2, vertex 3, 4, and 5. This corresponds to columns. The columns correspond to vertices 1, 2, 3, 4, 5. And the numbers here tell you which edges are present and with what weight. So for instance, this 3 here means that there is an edge from vertex 1 to vertex 2, and its length is 3. This number here says that there is a edge from vertex 4 to vertex 3 of weight -5, and so on and so forth. So that's what you have here. That's what you start with. And what you want is D super 5, which is the matrix of shortest path lengths from vertex I to vertex J for every such pair for which you're allowed any intermediate vertices you want. Because remember, because K is equal to N here, in this case, we are dealing with a graph with N vertices. So when you get to D of 5 for this particular graph, you are going to try all possible paths. And so you will get the genuine shortest path length in this matrix. And what the algorithm, Floyd-Warshall algorithm, does is it tells you how to go from D super 0 to D super 5. And that's what I'm going to explain next. And it turns out that the picture we had here is exactly the clue that we need to design the algorithm. We get 2 choices for every pair of vertices I and J. In the kth iteration, either the shortest path goes through K or doesn't go through K. If it doesn't go through K, you already have it figured out because it only uses intermediate vertices in the range 1 through K minus 1. But if it does go through K, it's simply a concatenation of 2 paths that you figured out already, which is the length of the shortest path from I to K and the length of the shortest path from K to J added together. So this gives us the necessary algorithm, which is shown here. It says for Floyd-Warshall's, let n be the number of vertices in the graph. That's the same as the number of rows in the weight matrix. We're going to initialize D super 0, which is the first matrix we saw on the previous slide. It's simply the weights of the edges that are present in the network. And then we're going to go through n iterations, and in each iteration, we're going to go from D0 to D1 to D2 to D3 to D4, all the way up to D super n. And in the end, we are going to return the matrix D super n. So the for loop essentially computes the matrix D super k, and this tells you exactly how to do it. So we're saying let D super k be the matrix of distances that we want, the shortest path lengths. then in each of these iterations, we're going to look at every pair of vertices. In order to look at every pair of vertices, we iterate through I and we iterate through j. So when I goes to 1 to n and j goes to 1 to n, we've essentially looked at all possible pairs. And this says that Dijk, so you have this formula here that tells you exactly how to figure this out. And this formula, it turns out, comes from this figure that we saw. So it says that either the shortest distance from I to j is what we've already figured out, or it goes through k. And you see that that's exactly what you see in the code here. It says that dij, the length of the shortest path from I to j in the kth iteration is either the same as the length of the shortest path from I to j in iteration k minus 1, or it is it's the sum of the distances from I to k and then k to j. Remember, that's what we saw in the network in the figure that I showed you. It's either this what we had figured out from I to j previously, or it's the sum of these two distances that you had figured out in the previous round. And so that's what you write here. Dijk is either Dijk minus 1, or it's the shortest, it's the sum of the distance from I to k and then from k to j. This is the option that's going to be true if the shortest path goes through k, and this is the option that's going to be true if the shortest path does not go through k. And by taking the minimum of these two, we're always going to pick the better of the two options. And so at the end of the, once k goes from 1 to n, at the end of the nth iteration, all these values are going to give you d super n, but it turns out d super n is exactly what we need because of the way we've defined it. It says that d super n is the matrix of shortest path lengths from vertex I to vertex j, for which all intermediate vertices are allowed, because this set is now 1 to 3 all the way up to n. So we structure the problem in a way that over time we get refined and more refined answers. And the paths that we consider become more and more refined. Well, actually, they get more and more generalized. And so in the end, we've tried every possible path, and we've written down the best one. But even though we are effectively trying every possible path, it's not an exponential time algorithm. It turns out to be very, very fast, because as we see here in the algorithm, there is only a single for loop that goes through n times. And inside it, there are two for loops that go n times. So it's n times n times n. It's an n cube time algorithm. And the algorithm is it's not very efficient, but it's about as efficient as it gets. Karne, Ningo, you've got to do something. All right, so this is a simpler way to write the Floyd-Warshall algorithm. It's actually more or less exactly what we did before. The only thing here extra is that there is some initialization that we do, and then the rest of it turns out to be what I've written here. There are 3 for loops, and then it simply says if there is a better, shorter, if there's a shorter path from I to j that goes through k, then go ahead and make that the best path. Otherwise, leave it as it is. That's all it says. So it's a very powerful algorithm, works very fast. Pretty much anyone can write this code in less than 5 minutes and can be reasonably sure it's right. You only have to add some initialization code here and you'll be done. So I'm pretty sure that all you guys are seasoned enough that you can write this code in any of your preferred languages in less than 5 minutes. But it's a fairly sophisticated algorithm. Trying to understand it takes way more skill than simply writing this code and getting it to work. And it's important to understand this because it has lots and lots of implications. There are many problems that can be fashioned out on top of this that you can solve. And as I said before, it's a really good example of this technique called dynamic programming, which is widely used in within computer science. More importantly, it's also widely used within these programming competitions that we are interested in. So that's the general idea. As I said before, the time complexity is n cubed, and there are many ways to improve the algorithm using something called fast matrix multiplication. Those methods are run slightly faster in at least in terms of time complexity, but don't always run fast in practice. And that's because these algorithms are very complex. And when you add up all the code that you write for taking care of all these details, it ends up being not as fast as we would like it to be. That's why these algorithms are only good if the matrices involved are extremely large. But if they're extremely large, you run into other hassles. And really, in the end, well, nobody ever really uses the fast matrix multiplication algorithms in practice. But they're great in theory for us to understand the limits of what we can do using good algorithms. And so I'm going to leave that with that thought. We really won't have a chance to look at these fast matrix multiplication, at least not for now. Most of the problems that you get in programming competitions don't require this extra matrix multiplication speed up component in order to get your algorithms to work right. So it turns out that the Floyd-Warshall's algorithm that I described very briefly here and in a little more detail here is enough for you to solve a lot of the all pair shortest path problems. So are there any questions? Okay. Looks like there are no questions. So let's go back to what we were saying. Remember, I told you briefly that this all pair shortest path algorithm, or rather Floyd-Warshall's algorithm, is really a dynamic programming algorithm. Now, what makes it a dynamic programming algorithm? It turns out that there are many features of your basic dynamic programming that are part of this algorithm. The most important part that makes it a dynamic programming algorithm is this step number 7. What you have here is called a recurrence relation, in the sense that you're trying to write down a formula for some value in the kth iteration in terms of values that you computed in the k-1th iteration. And this makes it extremely important because it almost feels like you're building up a solution. And over time, you will get better and better answers. And then finally, you will have the right answer that's needed by the problem. So this here is an example of a recurrence relation. You're writing down the length of the shortest path from I to j in terms of values that you computed previously. So either in terms of ij computed in iteration k-1, or ik computed previously and kj computed previously. When you put these together, it turns out to be a really powerful algorithm that you can use under many situations. There is another important property of dynamic programming that is used here, and that is to store intermediate solutions, or to store previously computed solutions. Here it turns out that you have to store the entire matrix that you computed in iteration k minus 1. Without that, you won't be able to compute the answers for iteration k, and therefore it builds one on top of the other and refines the answers as we go along. And that's another important feature of dynamic programming that I wanted to mention here. Uh, the so each iteration depends on the values that you computed in the previous iteration, but you know exactly how to start off the whole process by writing down what happens in dij0, which is simply given by the weight of the edge that may be present from I to j. So we know exactly how to start, we know exactly how to iterate, we know how to build up better and better answers, or better and better shortest path. And in the end, it's possible to prove theoretically that what you end up with in the distance matrix is exactly the right set of answers for the length of the shortest path between every pair of vertices. And so that's another important feature of dynamic programming that you will see here, namely storing previous answers or previous solutions, or in other words, things that you computed in previous rounds. And often you have to keep track of a lot of different things, a lot of different values from the previous round in order to make the current round successful. And it turns out here that you have to store all the n squared values from the matrix D from the previous round k minus 1. Without that, you can't get it to work correctly, at least not for all the values. The other important property that you need for dynamic programming to work is given by this picture that I showed you, namely that you have this property that says that the shortest path from I to j can be broken down into two other shortest paths, and these were which were computed in some earlier rounds. So that's why it's called the optimal substructure property, in the sense that every shortest path can be broken down into smaller pieces, unless that path itself is just one edge or something very simplistic. So these are all nice properties that will tell you immediately that you should be using dynamic programming. As you do more examples, this will start to become more and more clear to you. So much, that's all I'm going to say about why Floyd-Warshall uses this dynamic programming technique, and why it's a reasonably powerful algorithm for many of these graph problems. Are there any questions before I go on?
No, that made sense.
Okay. Anybody else? Clement, Harpreet, Patrick? All good? Are you guys awake, alive? I think I lost some of them. All right. So let me just assume that things are good, and let me move forward. So there is one more important topic in graph algorithms that I am not going to tackle anytime soon. That's the problem of network flow. Network flow is considerably harder than the problems we've seen so far. So that's going to take me an entire day to explain with a good example. Also, I want more of you to know it and to understand it and to use it and be comfortable with it. So I'm going to wait for another day when all of you are here to present that material. Also, it has connections to something called linear programming, which is an optimization technique. So I'll probably present both linear programming and network flow on 2 consecutive Thursdays, and make sure that all of you are are, first of all, you understand the theory, and secondly, you have some code that you can work, that you can get to work, and you can use in implementing some of the algorithms. So that's a very important topic, because there is almost no programming competition without a network flow problem. So if you want to really compete with the big boys, at some point you're going to have to learn network flow, and you're going to have to learn it well. Without quite understanding network flow, you're never going to be as competitive with the best teams. With enough knowledge of network flow and dynamic programming, you can start to compete with almost any team out there. The rest is really up to you to practice and become good at this. What else did I want to talk about? Uh, I think I'm going to stop here today and give you some problems for Saturday to work on during the mock competition related to any of these graph problems, and then if enough of you show up on the next Thursday, then I will talk about start to talk about dynamic programming. Dynamic programming is also an important topic. So I really want many of you to be there. These graph algorithms I presented so far, they're all fairly standard. They're in the textbook. Even if you don't know them very well, if you know how to program them, you can move forward. But for the other problems, both network flow and for dynamic programming, without really understanding the theory, it's going to be very hard to solve harder problems. So Lazaro, this is something that we should discuss when we should start to work on these so-called important topics, because attendance has been sketchy.
Yeah.
And it wouldn't make sense for me to cover an important topic that all of you really ought to know.
Yeah, I was thinking the exact same thing. Maybe same it for the fall.
Yeah.
These big topics.
Right. So what we could do in the remainder of the summer is to pick some easy problems to discuss here during these sessions. That way, even if you miss one or two problems, you're not missing a whole lot. But to really get to the theory, you're going to need. I'd like to make sure that all of you get exposed to it.
Okay. Yeah, that's perfect.
So, are you guys okay with stopping today, or do you have any thoughts, any questions? One more important thing is that you guys absolutely have to put in some time for Saturday mock competitions. I myself have not been diligent with setting problems there, but even whatever one or two problems I set there, you guys really haven't tried them. So it's unless that situation changes, it's not worth my time to put up the competition problems and try to move you guys forward. So how do we make sure that more of you come to the Thursday sessions and more of you compete on Saturday with the mock competitions? What should we do differently? Any thoughts, any suggestions?
I think we need to be pretty careful about the level of difficulty in the mock competition. Like, I feel like maybe at one point, like coming from not like a competitive programming, like I'm decent at data structure and algorithms, I would think, compared to most just random software developers. But in the competitive programming realm, like most people can go their whole career and never know how to do elite code hard. But I feel like sometimes like we'll get like 5 hards. What would be the equivalent there? And I think sometimes easy questions have been peppered in, but then those were a little too easy. So I think striking the right balance of, I don't know, I know Code Forces has like an ELO system and stuff. I think 11 to 1200 was on the hard side for what I considered that. But just speaking from like most of my experiences in leak code, I think somewhere in the medium range is a really healthy medium, which a lot of people can do.
Yeah.
But maybe some easies as well to make it more accessible for people.
Well, those are good points. However, to some extent, I have two different agenda items. One is to improve the general level of programming expertise, but the more important one, at least in my eyes, is to at least make some of you very competitive and to train you enough to be able to compete and represent FIU at these competitions. This is why I spend a lot of time with some of the theory to make sure that you're well-grounded, your foundations are good, and for the ones who want to train and be competitive, that's some of the Saturday sessions. I give you a mix of hard and easy problems. Now, just because I think something is easy doesn't mean it's going to be easy for you, and just because I think something is hard doesn't necessarily mean it's going to be hard for you. It's very hard to judge. It depends a lot on what kind of background you've had, what kind of problems you've solved. If something reminds you of some other problem that you've solved, then it suddenly looks easy, and you can handle it. So in the end, everyone has a bag of tricks that they apply to a new problem, and sometimes it works, and sometimes you end up struggling with it. Unless you guys put in the time, the situation is not going to change. So that's why on the mock competitions, I try to give a range of problems right from something that's very easy to very hard. So either people end up only solving the very simple problems, or one person goes and tries one of the hard problems and gives up. None of those things really are helpful. So that's why I'm asking for suggestions on how to tread that fine line, right?
Well, that's why, I mean, I said the level of leak code mediums is obviously pretty large, but there's definitely a level where I personally feel like questions can be reliably challenging, but if I wasn't able to solve them, I can still wrap my head around a solution. Or if I was able to solve it, it wasn't a waste of time because it was too easy. So I think just trying, as unsatisfying an answer that might be, I think, and obviously this is just me, but I think trying to hit somewhere in the middle is good.
Yeah, I have to say that I don't really visit lead code very often, so that's not something I'm familiar with. I could go and look at it, but unless it's available for me on Virtual Judge, I don't know what to do with them.
Oh yeah, sure. It's not specifically leak code. Like I just meant that difficulty level. The competitive programming, the leak code doesn't translate. It translates fine to competitive programming, but there's definitely differences. It's not as mathy usually. And the type of questions are more problem solving and less application of these algorithms.
Right. Once fall session starts, I will try to be a little more systematic. We've laid the foundations in terms of at least the graph algorithms, and what else did we do before this? Well, we did some of the basic algorithms as well, sorting and median and so on. So I'll at that point I'll start to go to some of the harder problems, but then there'll be a whole bunch of fresh new students who don't quite have the training, and it's going to be hard to balance even at the Thursday sessions to try and figure out what level to train you all at. We'll figure that out when fall shows up.
For me, so I'm not gonna lie, I've been lacking on the competitions lately because it's been pretty hard to try to handle everything. But I do believe from now on, things should be getting a little bit easier and should be
Okay.
participating. But
Okay.
in the past, when I looked at a problem and I attempted it and I couldn't solve it, I feel like it would have been really helpful if maybe we covered
We
those
had
problems.
solved it here. Yeah.
Yeah.
So
I can
that's what
at least-
I think that's my plan to tackle some of the problems here during these sessions, because we don't want to cover some good theory right now.
Yeah.
What we can do is to pick these medium, easy, medium, and a few slightly hard problems during these sessions, and at least you'll have recordings. The other people can watch them later and gather something from it. So I'm happy to do that, but I do need help from you guys, in the sense that I need you to suggest questions and problems that you have tried, because if you haven't tried them, then it's not useful for me to just give you a solution and say, hey, this is how you solve it.
Yeah.
I have something that helped me a lot was we stopped doing this, but there was a I'm scrolling through the Discord channel right now to see there was a beginner problems and a beginner and an advanced problems and a corresponding solutions thread in Discord. I thought that was a pretty good way of just making sure, and we usually did leak code questions on there. I feel like that was a really good way of just getting in practice, and it was super relevant. I remember specifically when you did the binary search section, that seeing there's a couple of range searching problems which I never thought to apply binary search to, and that like it took me a while to wrap my head around it, but I felt like I'm really good at those problems now because of getting the theory and then getting several corresponding daily challenges.
Yeah, so that's good. Then let's spend the rest of the summer looking at variety of graph and graph type problems, if that's okay with you guys.
Yeah.
Yes.
If I can get permission, I can share problems too on the Discord channel.
Yeah, please do.
Clement, hit me. Give me the power.
I think he's off. He's away from his desk.
Meditating. Yeah.
So yeah, send me suggestions of problems so that I can prepare and give you something useful on Thursdays, and then we'll take it from there.
Okay.
Yeah, sounds great.
Okay.
I'm not gonna do that, but I will ask for permissions from Clement and start doing those daily leak code ones to help from another angle.
Okay. All right. Then shall we stop here?
Yeah.
All good? Okay. All right, guys.
All right.
Have a good
Thank you,
evening.
Professor.
Take care.
See you all.
All right. Have a good night, guys.